Hello everyone. Good morning, good afternoon, good evening. Depends on when you're watching this lecture, as I always say. So now that we've started this, what do you call it, marathon? Yeah, it's a marathon of data structures. One data structure after another. So we did talk about three trees and some of the others. And in this lecture, I am going to talk about maps, hash table, and search trees. Might be optimistic, but we'll see. These are the three that I want to cover. It is a data structures class and algorithms class, so um, it's it. There shouldn't be any suspicion or surprise. There's a suspicion, but there shouldn't be any surprise that we're discussing about data structures. Why so many? That's a question that let me see. That when you initially start studying about classes, basic classes, first grade, second grade, whatever, the idea is to expose you to all these things and then figure out which one is useful to you at some point. Now, here, you looked at the data structures, or you look at the data structures at runtimes, how they're used, etc. And based on your use case, you will figure out which data structure you should be using. And you know what's going to happen at some point. You're like, this data structure is my favorite, or you'll be inclined to use two or three, which is perfectly fine. But overall, it's going to depend on your use case. What kind of speed you're looking for, and what kind of accessibility you're looking for. What's your use case? Okay. Having said that, let's jump right into it. Maps. What are maps? Maps use the concept of key and its value. Now, in our world, right outside of data structure, maps. You look at a map, will tell you how to go from point A to point B. Whereas this map here, it has two elements in it. One's a key, the other one's a value. So, and each key, first of all, each key's got to be unique, and each key will have a corresponding value. Okay, no two keys can have the same value. So keys are unique identifier. They are standalone by themselves, uh, and they'll tell you what the value is. Now the retrieval from map is fairly quick because it's indexed. So keys like an index, okay, key one, this is the value. Key two, this is the value. So it's literally like a map of key to value, right? That stores a pair. Um, some of the things to know, um, and these are built-in data structures that we're talking about. So they come with a whole bunch of functions for you to use, which is great. These are some of the ones from the C++ STL library. Java will have something similar, no doubt. So let's see. Begin. It returns an iterator to the first element in the map. N returns an iterator to the element one after the last one. Okay, not the last, but one after it. Try to output something at end, it's going to throw an error. Size, as the name suggests, returns the number of elements, the current number of elements. Max size, the max number of elements that a map can store. Try it out. I wouldn't tell you what's the max number of elements that you can store in a map, but this is something that you can try out on your own. Empty, it's a boolean, returns a boolean. Yes or no, simple answer, right? True, actually, true and false to be exact. If it's empty, it'll say true. Not empty, it'll return false. Pair insert, right? Map has a pair, takes in a key and a value. So pair insert, the insert method is going to take in a new element, the value and the map value, the key and the value. Erase takes in an iterator and will erase the element at pointed to by that iterator. Erase removes a particular key value from the map. Clear clears all the elements. Okay. Now let's see how this map is used. I'm going to show you the C++ example. No one has complained yet. Hopefully you guys are able to follow because Java is also very similar. And as long as you know the concept, conceptually you understand what a map is, doesn't really matter which language you're in. Okay, so you would include this library called map. The way you declare map is it's a key value. Key is a string in this case, and then maps to an integer. Okay, so it can be two different classes or whatever, but in this case it's a string and an integer. And the way you insert value is by using the subscript operator. MP, so the name of the map is MP, okay? And then you say MP at 1 equal to 1. MP at 2 equals to 2. And then an MP at 3 equals to 3. And then you say, then you declare an iterator, okay? And then you point the iterator to begin. And remember we said the begin method, what does it do? Points to the first element. Then you iterate, as long as it is not equal to mp.n, you say it at first, right? And then it at second. And then you increment plus plus it, right? So you're going to keep doing that, and as soon as you hit the end, and remember end is one element right after it, so by using the first, it second, you are going to be, it first is key, it second is value. So it still points to the key value pair, but that's how you get to it. See, there you go. Key 1, value 1. Key 3, value 3. Key 2, value 2. Okay. Let's go to another example. This example is a very simple one. All it does is shows you how to use the size method. So I've got the same map 1, 2, and 3, and what I do is I say map.size. Size of the map is 3. So now in here you've got the same map 1, 2, and 3, and then what I'm doing is map at 1, map at 2, map at 3. I'm using the subscript operator and I'm giving it the keys, right? And then if you want to check for a particular key, you say map.count at 4 greater than 0. Okay, mention the count method I didn't mention. Now what the count method does, it'll say, will tell you if 4 is there or not. Let me see if I have a better example of count. What is it? So it searches the container for element with the key, right, and returns a number of matches. Okay, so count is literally looking at the number of time for that it looks for the count of keys. So how many times do you have the key 4? Well, you have it 0 times. That's why the greater than 0 is not going to be true. Right? Key 4 is not in the map. Like if you said key 4 is in the map, I mean there should be 3. Right? Because it probably showed up once. This one is a slightly lengthy one, but some of the things I wanted to point out for a map is the declaration of a map, right? 2 integers. And in here I insert a pair. Okay, pair is another data structure. Pair can take in 2 types, okay? And in this case, 2 integers. So you insert 1 and 40. Key 1, value 40. Key 2, value 30. 360, so on and so forth. And another way of inserting a value into a map is the subscript operator at 7 equal to 10. And then you get an iterator here. Begin till the end plus plus iterator, I at first, I at second. What is this going to do? It's going to output the key value. Key value. Okay, now I have got another map. And what I'm going to do is I'm going to iterate. What do I do here? Assigning the elements from 1 to 2. So I declared a new one. So I'm using the copy constructor. I give it the beginning of quiz 1 and the end of quiz 2. Beginning and end of quiz 1. I've given that to the copy constructor, and what it does is it copies all the contents of quiz 1 into quiz 2, and then I output them. And then I erase everything. Well, not in this case, not everything. I erase from the beginning the instances of 3, right? So the key 3, I erase that key and value. Well, then I remove the key and value for 4. And then I look for the lower bound and the upper bound. Lots of things I do in here. Okay, using the iterator, I copy one from another. Okay, quiz 2 contains the elements of quiz 1. And then I erase 3 from there. And then I erase 4 from there. So quiz 1 has got 7 elements. Quiz 2, by using the copy constructor, it also has 7 elements in there, the same ones as that. If you remove removal of element less than 3, oh, you know I was wrong. Yeah, it actually removes. So erase take. What you could do is erase takes in the beginning, and then 3. So all the keys less than 3 are deleted. So 2 and 1 are deleted. Erase 4. What did it do? It only erased the key value, the key 4, and the value associated with it. Lower bound and upper bound, I mean, as the name suggests, lower bound of 5. Key 5 is 50. The upper bound of key 6 is upper bound 5. Key 6 element is 50. You know, upper bound and lower bound I haven't used that much. This is just so you know it exists, but can be slightly confusing. Okay, so now continuing on the discussion, let's jump into a hash table. Before, you know what? Initially, I was thinking that I'm gonna talk about hash table and then towards the end talk about the differences between the two. But you know what, Bunby? Because hash table is similar to a map when it comes down to it. But before we get into the nitty-gritty of hash table, it's good to know the differences between the two, because otherwise it can confuse you. Because they serve, I mean, overall, the reason it's a container to store um, data, and you know, there's keys and values in both. Now let's talk a little bit about the differences. Null keys. The map allows you one null key and multiple null values, whereas hash table doesn't allow any key or value, right? So keep this in mind. It's now you might be thinking of a use case of why you would have a null key with some values in a map, or because you might have a key which has null values, but why null key and with some values? I can't really think of a use case right now, but this is just a more syntactical thing that it allows you to do it. But hash table, no null keys or value whatsoever. Now one use case might be if you're looking for a data structure and you're going to store user inputs in there or something user interaction in there. You could use a hash table because you don't have to deal with null, right? If you don't want to deal with it, use hash table. The other thing is thread synchronization. Map is generally preferred over hash table if there's thread synchronization involved because the hash table is synchronized. Thread safe. Maps are not thread safe, whereas hash maps, hash table, are thread safe. Value order. Values are stored in sorted order in a map, whereas in hash table, values are not in sorted order. That's also another key difference, which is easier to remember. Searching time, right? Timing is very important. Um, you can use map or binary tree for smaller data because it's going to take log-in time. The number of inputs may be small enough to make this time negligible. But for large amount of data, um, hash table is preferred. Okay, so the two key ones that are easy to remember is the null. Hash table doesn't allow nulls in it, and then the sorting order. Those I think you can remember fairly easily. Um, let's talk about this as well. So hash table. There's the word hash in there. What is hashing? Okay, hashing is just a technique that maps a large set of data to a small set of data. Large, small. What does it mean? It does mapping to from keys to value, right? Similar to what you had before in the map. Now, what I'm thinking is if we go back in the map, um, what you had was you had keys and values. Here you have keys and value as well. However, there's a slight difference here. There is hashing involved. So hashing is the way you go from key to the value. That's what it's the mapping thing. Think of it this way, right? So there's keys in there's values, and hash function is kind of like the force that puts them both together. Okay. The value returned by the hash function is a bucket index for a key and separate chaining method. Each index in the array is called a bucket, and it is a bucket of linked list. So this is what hashing is doing for you. These are just some points to remember. There is hashing, there is rehashing, there is collision. Okay. So hashing does this mapping for you. Rehashing is a concept that reduces collision. Now, what's let's mention something about collision first. Collision is a situation when bucket index is not empty. It means that a linked list head is present at the bucket index, and we have two or more values that map to the same bucket index, right? So then you have to do rehashing to reduce this collision. So when you do that, it'll make a new array of double size and copy the previous array elements to it. So what it does is it resizes things for you, resizes your data structure for you, similar to a vector, because a vector is a dynamically sized array, right? And all you're doing here is by rehashing is you're increasing the size of it. So think of it rehashing as resizing, right? And it avoids collision. Now, when you do rehashing, that's something I'm not gonna get into it right now, but keep this in mind. You'll have to know when you have to do this rehashing. What else? Time complexity. The time complexity of hash table insertion and deletion is O of 1, right? Insert goes in right away. There's hardly any sorting, anything done, you just insert it. The worst case of it's linear. Best case O1. And then the time complexity of search, its worst case is linear, average is constant. Deletion, average is constant, worst is linear. Um, so this is also something to keep in mind when you're choosing the data structure. Now here, what I was going to do initially is I was gonna go and talk through each and every pieces of this implementation. So what this is a hash table implementation using a linked list. Okay, so I've got a node in here which you're familiar with. It's got a key, value, and then pointer to the next one. And then I have a set node. It takes in a node, key, and a value. So it sets the key, value, and then the pointer to next. Um, and then there's a num elements. There is a initialize hash map, and there's a hash function in there which does the bucket thing that I was talking about. There's insert in there. There's delete in there. Um, there's search in there. Now there isn't an easy way. There isn't an easy way to explain this. What I'll put it out there, um, in the announcement or under the course material, so you guys have access to it. But what you should do is go through this example, right? Go through this how it's implemented because the book doesn't have this implementation that I'm sharing with you. So keep this in mind. Go through it and let me know if you have any questions. But the driver, it creates the hash map, right? And then it inserts a value. This is the key, this is the value, right? MP is the hash map key value. So it does this key value pair. And then it does a search and it does deletion as well. So insert, search, deletion. And all of those methods are defined here. Right, delete is here, um, insert is here. So I'll put it up there, and then um, and then go through it. Okay. Now let's jump into AVL trees. We did talk about binary search trees, but we didn't talk about AVL trees. And depending on time, although I doubt it, I'll get into red-black trees. If not this, then maybe next lecture I'll touch upon them because that's another interesting tree. Now, AVL tree. It's a self-balancing binary search tree. So it's a type of a search tree that balances itself, in which each node maintains extra information called a balance factor, whose value can be either -1, 0, or +1. So you should keep that in mind that the balancing of each node, the value should be -1, 0, or +1. I'm going to go through some textbook type of explanation for balancing factor, and then we'll walk through an example which will illustrate how we go about doing this. So, balancing factor of a node is the difference between height of the left subtree and that of the right subtree. Balance factor is equal to height of left subtree minus height of right subtree, or right subtree minus left subtree. Now what should happen is at the end you have to either get -1, 0, or +1. Pictorially, when you see this, it'll make sense. But right now you're looking at it, huh? So you take the height of left subtree and then the right one, you subtract that, or the right, take it out of from the left. So you should either have 0, +1, or a -1. In simple terms, is you can only have, so you cannot have a disbalanced tree. So at any moment in time, what's going to happen is your left subtree will be greater by one node or less than by one node as opposed to the right subtree. Okay? So either all the nodes, leaf nodes, are going to be balanced or they're going to be off by one. It's as simple as that. Now let's take an example for this. So you've got this tree right here. Well, the example is going to come next. This is what the balance tree looks like. Now look here. these leaf nodes, or this leaf node, this one, they're at the same length. And this one is one more than the previous one. That's about it. So you won't have a scenario where 21, 11, and then it has another child right there. Looks looks decent. So that's how you balance it. Um, Now the way you go about doing this is via a left rotate and a right rotate. Okay? So when you insert nodes, you would do a left rotate or a right rotate up until you get that balance factor of 0, -1, or +1, right? There is also a left-right rotate, right-left rotate that I'm going to touch upon. But let's not talk about that yet. Let's understand what the left rotate does. So you guys have the eventual goal in mind, right? Is balance factor. In the left rotation, the arrangement of the nodes on the right is transformed into the arrangements of the left node. Look at this picture right here. So you've got X, which has got children A, Y that's got children B and Y. Okay, so you want to rotate left. If Y has a subtree, assign X as the parent of that subtree Y. If the parent of X is null, make Y as the root of the tree. Else, if X is the left child of P, make Y the left child of P. Else assign Y as the right child of P. So you separated X and Y right here, right? The reason I've got so many pictures here, you'll see more of them, is to make the understanding easier for you. Pictures worth 1,000 words, because this can be a tough one to grasp. Because these are all rules, but pictorially you can see how changes are coming about in each step. Now you'll make Y the parent of X. So we started off with this, right? We're making Y the parent of X, right here. A's got children A and B, Y's got Y. Same thing, A's got children A and B, Y's got Y. We haven't touched the children yet. Okay? So that's what essentially happened. So you started off with this right here, and you rotated left, meaning you brought Y up and you brought X down. And pictorially, this is what you ended up with. Oops. Right here. Okay? Children are the same, but we rotated left with Y was down here, X was a parent, we brought Y up. That's left rotate, right rotate. Now let's look at this scenario. So this is your starting tree. Y has got a child A, X has Y and B. If X has a right subtree, assign Y as the parent of the right subtree of X. X had Y, right? It's still keeping the same for now. Y's got B and A. X didn't have a right subtree, don't do anything. If the parent of Y is null, okay, makes X as the root of the tree. Else, if Y is the right child of its parent P, make X as the right child of P. Otherwise, assign X as the left child of P. So I've got these two detached for now. Make X the parent of Y. Right? So we're rotating right, so X came up. And this is what you ended up with. And then there's a left-right rotate and a right-left rotate. It's a mouthful, but in left-right rotation, the arrangements are first shifted to the left, okay, and then to the right. So there's two shifts. First, you do left rotate, and then you do a right rotate. Whereas the right-left is the opposite, right? You would do a right rotate and then the left rotate. And you do this kind of rotation up until you get that balance factor figured out. So the rotation, I don't think book talks about it, but the insertion it does talk about in like algorithm manner. So a new node is always inserted as a leaf node with a balance factor equal to 0. Okay? That's what you want to try to do. Go to the appropriate leaf node to insert a new node using the following steps. So you're getting the new key. You compare the new key with the root key. If the new key is less, then call insertion algorithm on the left subtree until the left node is reached, okay? So it's recursion. Else, if new key is greater than the root key, call on the right subtree until leaf node is reached. Otherwise, you just return the leaf node. Compare the leaf key obtained from the above steps. So once you follow those steps, you'll get the leaf key. If the new key is less than the leaf key, then you'll make new node as the left child of the left node. Otherwise, new node is on the right child. And then you would update the balance factor. And then remember, height of left minus height of right, or height of right minus height of left. So you want to always keep the update balance factor updated. If the nodes are unbalanced, meaning they're not 0, negative 1, or 1, then if the balance factor is greater than 1, it means the height of the left subtree is greater. So you've got a long left subtree. So you do a right rotation or a left right rotation. If the new node is less than left child key, do right rotation. Otherwise, do left right rotation. If the balance factor is less than negative 1, what does it mean? That means your right subtree is great, right? You've got leaves in there. So you do a right rotation or a right left. You do a left rotation if the new node key is greater than the right child key. Otherwise, you do a right left rotation. Okay. I think I'm going to stop here for now. I'll post examples up for the AVL tree and Java and C++, so you guys can look at it. So you'll have 3 examples, right, for today's lecture. The first one that I mentioned is going to be up there. The linked list representation, right, for the hash table, and then you also have the representation, the implementation for AVL tree in Java and in C++. For the hash table, it's only going to be in C++, but it's similar syntax. You guys will be able to figure it out. All right, so that's it for this class. I'll see you guys in the next one. Take care.